Water. It works in many ways, seen and unseen, that affect our lives. This is the story of some of those ways. The story of water in the forest. Did you ever wonder where the water that you use comes from? You might be surprised to learn that most of it comes from forests, where many of our streams have their source. Since 1951, researchers at this laboratory have been studying what happens to that water. Working in the Furneaux Experimental Forest in Parsons, West Virginia, on natural drainage basins called watersheds, measuring precipitation, stream flow, and erosion and sediment, analyzing water quality, and studying the impact of man's activity on water resources. From their work and that of other scientists, we're learning some of the secrets of water in the forest. Since the Earth's beginning, water has circulated in what is called the hydrologic or water cycle. The energy of the sun lifts moisture from the earth by evaporation and from plants by transpiration. The force of gravity brings it back as precipitation and moves it over and through the land as stream flow and groundwater. Water comes to the forest as precipitation in the form of rain, sleet, hail, or snow. It is measured by instruments placed in openings like this one, so that trees won't affect the measurement of precipitation. The standard rain gauge collects rain in summer and snow in winter. The recording rain gauge responds to the weight of precipitation and records a line on a chart that shows when and how much fell. Intensity in inches per hour also can be determined. From the data collected by these and other instruments, long-term records have been compiled, showing annual variations and cyclic patterns. Not all water reaches the forest floor. Some is intercepted, clinging to plant surfaces and evaporating when the storm is over. In hardwood forests, about 13% of the annual precipitation is intercepted, 16% in summer, 10% in winter. But mature conifers with year-round foliage intercept as much as 25% of the annual precipitation that falls on them. The water that falls or drips through the tree canopy and reaches the forest floor is called throughfall. Most throughfall readily soaks into the litter-covered forest soil, where it eventually becomes water for vegetation, stream flow, or groundwater. Most of the precipitation intercepted by plants, along with water or other wet surfaces, such as the forest floor, is lost to evaporation. Evaporation is the process by which water is changed to vapor and returned to the atmosphere. The amount of loss is measured by evaporation pans. Transpiration is a special form of evaporation, in which water in the soil is taken in by roots, then pulled up through the stem to the leaves. There, energized by the heat of the sun, it vaporizes. Thus, leaves act in two ways to return water to the atmosphere: by evaporation of intercepted water and by transpiration of water taken from the soil. One of these containers is filled with sand, the other with gravel. Which one do you think will hold more water? Surprised? This cylinder has less water in it. You see, the sand held more water because it has more pore space, room between particles. Pore space and other soil properties play important roles in controlling what happens to water in the forest. Soil is the material above bedrock. It is composed of 3 different size particles: sand, silt, and clay. Sandy soils have a predominance of large particles. Silty soils have intermediate-sized particles. And clay soils have small ones, so small that individual particles cannot be seen with the human eye. The percentages of sand, silt, and clay determine a soil's texture. Sandy soils are coarse textured. Clay soils are fine textured. The way these particles are arranged, the soil structure, together with its texture and pore space, determine the moisture holding capacity, the amount of water that can be held in the soil at a given time. Water seeps easily through wet soil, but in drier soils it is held tightly so that it resists the pull of gravity and movement through the soil is slowed or stopped. Depending on structure and texture, a foot of dry soil can hold from 2 to 5 inches of water. The amount of water left in the soil about 48 hours after a soaking rain is called the field capacity. It is greater in fine-textured soil than in coarse ones. But not all this water is available to trees and plants. As soil dries, it can bind water more tightly, leaving less available to plants. When plants reach their wilting point, they can die for lack of water. Soil moisture can be measured in several ways. One way is with a neutron moisture meter equipped with a probe that can be lowered to different depths. Radioactive neutrons emitted from the probe measure the soil moisture, which varies in response to precipitation, transpiration, and season of the year. The depth of soil also affects its capacity to hold water. Deep soil provides plants with more water for growth than shallow soil of the same texture. To understand what happens to water in the forest, we also need to know how it moves from the forest floor, through the soil, to streams. This stream flow is what's left from precipitation after other water losses, storage of moisture in the soil, and evaporation and transpiration are deducted. Less than half the water that falls on forests becomes stream flow, so these other deductions are substantial. A much smaller percentage of precipitation is returned as stream flow in the summer, when trees are transpiring rapidly, than in winter when transpiration is low. Runoff produced during storm periods, storm flow, accounts for about 20% of forest stream flow. Storm flow is the result of 3 processes: precipitation falling directly into stream channels, subsurface flow moving through the soil, often through root channels and animal burrows, and overland flow across bare, exposed ground. The litter layer of the undisturbed forest protects soil from the force of the rain and keeps soil pores open. Furthermore, the capacity of the soil to absorb moisture is almost always greater than the rate of precipitation, so overland flow is rare on forested slopes. Runoff produced between storms is called base flow. and accounts for about 80% of forest stream flow. Base flow comes from springs and the slow drainage of moisture from the soil. This is a stream gauging station, one of several devices used by forest hydrologists to measure stream flow. Runoff from a watershed is channeled into a weir pond to reduce its velocity and through a V-notch so flow can be measured. The weir pond and the stilling well are connected by pipes so that water levels are the same. A float in the stilling well is attached to a water level recorder in the gauge house, which records changes in water levels over time on a chart. This pen trace is called a hydrograph. This hydrograph indicates that stream flow increased soon after precipitation began. Peaks on the hydrograph indicate the time and amount of highest stream flows. The amount of stream flow depends not only on precipitation, but on the type of vegetation on the watershed. Grass-covered watersheds normally yield more water than tree-covered ones. Forest-covered watersheds produce the least stream flow because trees use large amounts of water. Watersheds covered with conifers produce less stream flow than those with hardwoods, since they intercept about twice as much water and keep their needles year-round, transpiring moisture when hardwoods are dormant. Stream flow is also affected by tree cutting, which reduces transpiration and interception, and temporarily increases soil moisture content and stream flow. In humid areas, rapid regrowth occurs, and water yields soon drop, returning to normal in 5 to 6 years after cutting. The flow of water since time began has left its mark on the land, sometimes cutting deep canyons or winding meanders through the landscape. These patterns result from gradual erosion, the process by which soil material, sediment, has been carried away over time. Accelerated erosion seldom occurs on undisturbed forest soil because, as this infiltrometer shows, soil with a litter cover absorbs water rapidly. But when mineral soil is exposed, raindrops, acting like miniature bombs, dislodge materials that can then become embedded in pores and seal them off. This reduces the soil's ability to absorb water and leads to overland flow and accelerated erosion. Even in forests untouched by man, there are natural sediment sources, especially along stream banks. And when it rains hard enough and long enough, the result is erosion of the stream channel. When the litter cover is removed, the texture and rock content of the soil determines much of its potential for erosion. Fine-textured soils like clay and those with low rock content are more likely to erode than soils with a higher rock content. Stones sometimes hold the soil in place, forming pedestals and eventually an erosion pavement. This stream gauging site also is equipped with devices to measure sediment loss. Coarse materials that move along a stream bed load, are trapped in a sediment box and removed for weighing. Fine organic and inorganic particles suspended in water are collected by a Coshocton wheel, which diverts a small percentage of stream water into a sediment collection tank, where samples are removed periodically. In a lab, the cloudiness produced by suspended particles is measured with a turbidity meter, and the the sediment is filtered out and weighed to determine its concentration and calculate how much suspended sediment is transported from the watershed. Most sediment is exported during storms, reaching its maximum concentration and beginning to decrease before stream flow peaks. Roads can be a primary source of sediment in forest streams. They can be equipped with devices to measure erosion. A common method is to install erosion plots in roadbeds with a collector trough so sediment-laden overland flow from the plot can be diverted to a tank where samples can be collected. The annual sediment production is usually very low on undisturbed forest watersheds and is also low on carefully logged areas with appropriate buffer zones near streams. But if care is not taken, especially with logging roads near streams, sediment levels can be high, harming fish and limiting recreational use. The way water is used determines the quality needed. Water for one purpose, irrigation for example, may not be good enough for another, like drinking. And the quality of water will be affected not only by things we can see, such as sediment, but also, and even more important, by things we can't see. Temperature is one. If streams get too warm, some species of fish, like trout, can't survive. And dissolved materials, substances visible only by chemical analysis and the use of sophisticated electronic equipment, can affect water quality. One of the important measures of water quality is its level of acidity, expressed in pH units. As pH decreases, acidity increases. The acidity of water affects its usefulness for many purposes, including its ability to sustain plant and aquatic life. Another important characteristic is the water's electrical conductivity, an index of the amount of dissolved minerals in it. A low conductivity can make a stream infertile. Too high of a conductivity produces poor water quality. The forest makes natural changes in water that passes through it. As precipitation enters a tree canopy and becomes throughfall, water passing over its surfaces dissolves particles and changes its chemical content. Geologic materials produce additional changes in the water as it passes through the soil and over rocks. Because of these changes, most of the naturally occurring elements in a forest can be found in its water, dissolved in the form of ions. Samples to be analyzed for water quality are gathered in several ways. A wet-dry collector captures precipitation in the open, and a through-fall collector catches it under a tree canopy. Grab samples can be used to collect stream flow, and automatic pumping samplers are especially useful during storms. Lysimeters, buried in the ground, provide samples of soil water by catching seepage and delivering it to an outlet for collection. Continuous measurements of stream water characteristics are also obtained. Automatic instruments record direct measurements of pH, conductance, and water temperature. In addition to natural changes, man's activities can also dramatically affect stream water chemistry. In the eastern United States, air and water pollution both have an impact on stream water chemistry, and both pose a threat to forest ecosystems. Rainfall in the east is acidic, partly because of acid-forming compounds present in air pollution. During storms, these acids are carried to earth as rain and snow. While scientists have found that precipitation falling on the Furno watersheds becomes less acidic through natural processes as it passes over and through vegetation, soils, and bedrock, the forest's ability to neutralize or buffer these acids is limited. Therefore, the soils and stream water could become more acidic over time and may eventually slow forest growth or harm aquatic life. Drainage from active or abandoned mines also can affect forest streams, producing high levels of acidity, which will not support plant or animal life. In contrast, some of man's activities have small or only short-term effects on streams. Logging usually does not cause significant changes in stream flow chemistry, and buffer strips with shade trees prevent temperature increases. Aquatic organisms can thrive when care is taken to maintain water quality. Forest researchers are still working, still learning. And from their patient efforts, we understand some of the ways in which water affects a forest, and the forest affects water. We know something about precipitation, evaporation, and transpiration, soil moisture, stream flow, erosion and sediment, and chemical actions that affect water quality. An understanding of these processes is helping foresters make decisions which protect two of our most valuable natural resources, our forests and our water.